Yes, I am Thomas Saller, and as he said, I'm talking about an asymptotic homogenized simplified P2 approximation to the neutron transport equation. For those of you that are not aware, I have been sick for the past few days, so if I take a short break to cough everywhere, it's not because I'm stalling for time, it's because I'm sick. Also, if you feel the need to cough during my talk, feel free. I believe that's karma. Okay. So today I'm going to start by talking about just neutron transport in general, since all but one of you are not reactor physicists. And then I'm going to go into the asymptotic analysis that went into developing this method. That's something that I could spend 30 minutes talking about the math, but I don't think anyone wants that. If you do, ask me later. And then I'll go into some sample results with the new method, and then finally talk about conclusions and future work. So first, introduction to neutron transport. What is neutron transport? It's essentially the study of the motions and interactions of neutrons with matter. And when I talk about neutron transport, I talk about it in kind of a macroscopic scale. So I'm not interested in exactly how a neutron goes into an atom, a nucleus, and then spits out, I don't know, a gamma ray or something. I'm more interested in if 10 to the 15 neutrons hit some polyethylene shielding, how many are going to come out the other side and with what energy. And neutron transport can be used in a few fields. So reactor physics is mostly what I do. That pretty one is about reactor physics. So with that, we look at neutron densities inside a reactor and try and get power profiles so you can tell whether or not the reactor is going to be safe. Shielding is another very important one. It's that pretty picture. So with shielding, you're worried about neutrons coming from some source, from a reactor, from, I don't know, secret materials, and then you want to make sure that you can protect people around you. And then radiation monitoring, that has to do with, if someone's trying to smuggle some nuclear material into the United States, how do we detect what's in there? And so I'm talking about neutron transport here, but gamma transport and electron transport are all very related and are also all important to all three of these. Okay, so quantities of interest. These are all the things I care about, and they mean a lot to me. So the angular neutron flux is the first one. That's just the product of the neutron's velocity with the neutron density in the reactor. And so that's a function of space and angle and energy. When I say angle, I mean the angle that the neutron is traveling. Then we have the scalar neutron flux, which is just an integral over all angles of the angular neutron flux. We have macroscopic cross-sections. Those are essentially a probability of a certain reaction rate or reaction type per unit length. And if you multiply your scalar neutron flux with your cross-section, then you get the reaction rate. So that's how you know things like fission rates in the reactor, things that we care about. And then finally, there's the core eigenvalue. And that refers to how a neutron population is changing in a reactor over time. So when you hear the word critical referring to a reactor, that actually means that K is 1 and that the neutron population is steady. So that's a good thing. Supercritical means that you're getting more and more neutrons and it might explode. Subcritical means it's dying away. Okay, so this is the equation that I have devoted my graduate school to. It's the Boltzmann transport equation for neutron transport. It's a balance equation. So on the left, we have losses. On the right, we have sources. So for losses, we have our streaming term, neutrons moving in and out, and then our collision term. So anytime a neutron collides with an atom, it's removed. And then for sources, we have scattering sources. So neutrons that have a certain angle and energy that hit something and then have a new angle and energy. And then also the fission source. So it's a fairly difficult problem to solve. It's 6-dimensional. It's 7 if you add time, which I don't. The solution is not smooth at all. And cross-sections, they're measured quantities. I'm sure lots of you know about this, and they have uncertainties. And so you can never believe any, even if you could solve this perfectly, you could never fully believe the answer. Okay, so how do we solve that equation? We clearly can't just solve it directly. You can't integrate something and then have the answer. There are three main ways we solve them, or solve it. The first is Monte Carlo. It's a very popular method where you use random numbers to simulate individual neutrons. And then, so you just follow a neutron as it goes through a reactor or something until it dies. And then you do that millions and billions of times, average the results. And that works because the Boltzmann equation essentially represents like the average behavior of neutrons in a reactor. And then there's the poorly named transport methods, approximations to the transport equation. And with those, you just discretize the equation in time, energy, angle, space, and then solve all those resulting equations. So examples of that are discrete ordinates and method of characteristics. And then finally, the one that I'm more interested in is spherical harmonics based. And with that, you use a spherical harmonic expansion of the angular flux to eliminate the angular variable. And so then you still have to discretize the equation after you do that, but you have a smaller phase space because you don't have to worry about angle anymore. And you're left with more equations to solve. There are a couple more. I did something. Okay, there are a couple more things of interest. So homogenized neutron transport. The problem with all the methods I just talked about, is that they can be very computationally expensive. So if you have a full 3D reactor, you can have upwards of 10 to the 13 unknowns, which would take forever to solve, especially on a single PC. So what we can do is called homogenized transport theory, where we look at a single assembly, a 2D slice of a single assembly, and just perform a calculation on the assembly by itself with reflecting boundary conditions. Reflecting boundary conditions essentially means that this assembly is repeated infinitely. And then once you solve that problem, you use the resulting flux to go from having cross sections that have some spatial variation in the assembly to just a single one for the entire assembly. And then you go and solve your full core, and it takes a minute rather than days. And the reason we need to do this is if you have accident scenario calculations you want to do, those you're going to have to perform a full core calculation every millisecond or something, and it can take a very long time, especially when you combine it with thermal hydraulic calculations. And then finally, this one's more motivating for my work. It's the 2D, 1D method. So it's in between homogenization theory and full core transport. What you do is you look at a full core and then just look at 2D slices in it. And so you solve those 2D slices with some transport method like MOC. And then you couple all of these planes together with some low order transport method. And so SP2 is a potential low order transport method. So from here on out, I'm going to be talking in 1D rather than the full 3D, both because it's easier to explain and because our eventual motivation is to use SP2 as the 1D part of 2D, 1D. Okay, so the asymptotic analysis. This is the math, but there's not going to be much math. So the general idea in the asymptotic analysis is that you have a single unit cell. So this would be just like a reactor pin. And it's repeated a bunch of times, n times, with n large enough such that 1 over n is a very small number, epsilon. If we have this, then we can assume that our angular flux is a function of two separate spatial variables. The fast one, y, which refers to variations in a pin, and then the slow one, z, which would be variations over the entire core. So if we do that, we can rewrite our angular flux as a function of both those variables and do an expansion in epsilon, our small parameter. And then you plug that back into the transport equation. It gets really messy, but then you just look at the parts that have the same orders of epsilon, so all the ones with epsilon to the 0, epsilon to the 1, so on and so forth. And if we look at just those, we have some nice clean equations where L is given here. And you can solve these one by one. So the nice thing here is that to solve for psi 1, it's just a function of psi 0, which we solve for up there. So most of what I did theoretically is solving these sequentially. And while you're going along, once you get to n greater than 2, you have a problem where this might not have a solution. And so to force it to have a solution, you have to integrate the right-hand side over space and angle, and that has to equal 0. And that's what we call a solvability condition. And the solvability conditions are nice because they give us equations that we want. So this is one step below SP2. This is diffusion theory. So if we look at the solvability conditions for just psi2 and psi3, we get the diffusion equation with a diffusion coefficient that is unique and complicated, and I didn't write it down. And you also, if we go back to our expansion of the angular flux, we get it in terms of these weird f functions that I'm not going to go into, and the result from our diffusion equation, the solution and the derivative of the solution. And this is actually very interesting because normally when you do diffusion theory, and diffusion theory is kind of the workhorse for full core calculations, you assume that the angular flux only has the first term. So already with this method, we've added a correction term to the angular flux, which we'll see how significant it is in a second. So then if we go further, psi4, psi5, we get the SP2 equation, which is a fairly simple differential equation. Once again, the diffusion coefficients are complicated functions of a bunch of f functions. And now our angular flux has 4 terms in it instead of 1 or 2, including second derivatives and something that is based on the core eigenvalue, which is pretty unique. Okay, so now that I've kind of introduced the methods, I'm going to just show a couple results. I have a million results, but they all basically look the same. And so I'm going to just not punish you too much. Okay, so what I did for some of the early ones is I would look at a single pin cell, like I was talking about earlier, and then set multiple side by side, try and solve it, see what sort of result we get. And the thought is that as you add more and more pin cells, diffusion and SP2 should get more and more accurate because it's like it's getting closer and closer to an infinite medium, and diffusion and SP2 can solve that exactly. So I had to put this here because eigenvalue differences are very important in reactor physics, and this means a lot to me. This is a very good table that looks meaningless. So HD and HSP2, those are the standard diffusion and SP2 that people do now. AHD is asymptotic homogenized diffusion, and that was something that I got along the way while trying to obtain asymptotic homogenized SP2. So these are errors in %milli, which is where you subtract from the reference eigenvalue and then multiply it times 10 to the 5th. So it's 1,000th of a percent. And you can see that as you go from any of the standard ones to the asymptotic ones, especially asymptotic SP2, when you have very few pins, which is when these methods should be bad, you get improvements of factor of 2 or more, which made me very happy when I first saw this. Better representation is in this plot. So this is a ratio of the SP2 or diffusion flux to the reference solution. So 1 means that it's giving you the exact result. The jagged line is what you get with standard diffusion and SP2 theory, and it looks terrible. This bumpy one is just asymptotic homogenized diffusion. So that's when you have that 1 additional correction term. And then when you add the 2 other correction terms, you get a very, very smooth result that's very close to the actual solution. So all the other plots that I could have shown you would look basically just like this. And then there's one other important factor when you're doing these calculations. It's discontinuity factors. Essentially what they do is the diffusion and SP2 solutions, when you solve your equation, if those are continuous, then your angular flux, your reconstructed angular flux might not be continuous. So the idea is that you let these smooth lines are your diffusion or SP2 solution. So you let those be discontinuous at a surface so that when you use the equation to get the angular flux, that whole thing is continuous. And that's what you actually care about. So basically, you're just ensuring that some moment of angle is continuous at the surface of an interface. And so I thought this was interesting only to me. So this was another test problem that's supposed to represent a light water reactor core. So it has a bunch of different assembly types. You got some gadolinium in there as a burnable absorber. You have mixed oxide fuel and uranium oxide fuel. And what we see here is that the choice of discontinuity factor doesn't really matter for diffusion, but for SP2, you can get a lot better results with higher order, so mu squared discontinuity factors, even though you get some weird jaggedness in there. So, yes. Okay, so on to conclusions and future work. So in conclusion, I did derive asymptotic homogenized SP2 equation, as I said, and an equation for the corresponding reconstructed angular flux. And that's what was giving us actually the really good results. And then in a long series of 1D test results that I showed a couple of, we consistently saw that the AH SP2 is better than the others, and that even asymptotic diffusion is better than what they are currently doing. And then finally, that the choice of discontinuity factor is very important and actually rather ambiguous. So that's part of what I'm looking at right now. And finally, future work. So 1D is kind of what we want for the 2D 1D method, but do need to go to multi-group, which essentially is more energy groups. And we've done that with homogenized diffusion, so we just need to apply probably the same procedure for SP2 and then get it to actually work with 2D, 1D, and then maybe graduate, probably not. Okay, so I would like to thank my advisors who taught me quite a bit, and then the other people at Michigan that taught me everything else, and then of course Corel and the SSGF for all their support over the years. And then, because I'm the last one of us, I get to be sentimental. And thank you guys. Well, and you, but I thanked you a second ago. Okay. Questions?